Have you ever wondered what a bit is and how a CPU processes data at the bit level? What exactly is the scene behind the coding language? Today, we're going to break down some of the most important concepts in the world of bits and CPUs. After this video, we'll guide you through building compression software with encryption using AES encryption and zip compression in Python with the help of the Bitwise AI agent. This will help you to understand how to encrypt, decrypt, compress, and uncompress binary data. We're condensing a whole 4-year computer science degree into a 6-month course. These days, with AI, you don't need to code everything yourself. What's more important is knowing how to instruct AI to code for you. That's why mastering the core concepts of computer science is key, rather than focusing on coding skills alone. To really get the most out of this, watching the video isn't enough. Be sure to follow the steps, complete all the tasks, and finish the project outlined in the video description. Now let's get started. Learning how a computer works might seem complex, but using the first principles thinking approach, we can break it down into simpler concepts. First, let's consider how computers process data. To do that, we need to understand what kind of data a computer can access. Before computers existed, in 1725, people used punched tape to store data by making small holes in paper. This technique was originally used to control machines like looms and later for tasks like distributing music and sending telegrams. By the 1970s and 1980s, punched tape became a common way to store and transfer binary data to early computers. Each hole in the tape represented a 1, while no hole represented a 0. This system of ones and zeros is called binary, which is how computers naturally store and process data. As technology evolved, punched tape was replaced by magnetic tape, and then by magnetic disks, but the core idea remained the same. Data was stored in binary. On magnetic media, a magnetized area represents a 1, and a non-magnetized area represents a 0. In today's computers, data is stored and processed using electrical signals. An on signal represents a 1, and an off signal represents a 0. Since binary only requires 2 states, 1 and 0, it aligns perfectly with the way machines operate, keeping the electrical circuits simple and efficient. But how exactly does the computer process and store these zeros and ones in the CPU? To understand how computers process logic, we can start by looking at simple circuits. Imagine a circuit where 1 or 2 switches act as inputs and a light acts as the output. We define a closed switch as 1, on, and an open switch as 0, off. Similarly, if the light is on, the output is 1, and if the light is off, the output is 0. By turning the light on and off using these switches, we can simulate how computers handle logic. In the first example, we connect 2 switches, A and B, in series with the light. The light only turns on, output 1, if both switches are closed, when both inputs are 1. This is called an AND gate. In programming, we write this as A and B. Both inputs must be 1 for the output to be 1. Next, we connect 2 switches, A and B, in parallel with the light. In this case, the light turns on if either or both switches are closed, when the input is 1. This is called an OR gate. In code, it's written as A vertical line B. If either or both inputs are 1, the output will also be 1. In the third example, we have just one switch, A, and the light is connected in parallel. When the switch is open, 0, the light turns on, 1. When the switch is closed, 1, the light turns off, 0. This is because when the switch is closed, the voltage at both ends of the light is the same, so it doesn't light up. This is a NOT gate. In code, we write it as wavy line A. If A is 1, the output is 0, and if A is 0, the output is 1. These 3 gates, AND, OR, and NOT, are the fundamental logic gates used in CPUs. By combining them, we can create more complex gates, such as the NAND gate, the inverse of an AND gate, the NOR gate, the inverse of an OR gate, the XOR gate, which outputs 1 only if one of the inputs is 1 but not both, and the XNOR gate, which outputs 1 if both inputs are the same. One important gate in coding is the XOR gate, written as A(B). This gate outputs 1 only if A and B have different values. We'll discuss how XOR is used for data encryption later on. In actual digital circuits, including CPUs, we use CMOS, complementary metal oxide semiconductor technology, to implement these gates. In CMOS circuits, switches control the on-off signal through electrical voltage. Using combinations of these logic gates, we can build any digital system, from simple circuits to complex CPUs. A modern CPU contains billions of logic gates that perform various functions, such as data storage, arithmetic operations, decision-making, and timing control. So these logic gates are the building blocks of how computers process and work with binary data at the most basic level. CPU registers are small, fast storage areas inside the CPU that temporarily hold data, instructions, or addresses during operations. These registers are built using logic gates, mainly flip-flops or latches, which are created from combinations of AND, OR, NOT, and NAND gates. These flip-flops store binary data, zeros and ones, and can be controlled to store, read, or reset data as needed. A register consists of multiple bits, with each flip-flop holding 1 bit. By combining multiple flip-flops in parallel, you get a register that can store more data, several bits at a time. In the following x86 assembly code, we load an immediate value of 1234 into the AX register. In a high-level language like Python, we can achieve the same thing by simply assigning the value 1234 to a variable a. In assembly, Python, and other languages such as C or C++, we can write the decimal number 1234 in binary format with the prefix 0b, or in hexadecimal format with the prefix 0x. Eventually, during runtime, the Python interpreter will load the value 1234 into a register behind the scenes. So you can think of the variable a in a high-level language like Python as similar to a register in assembly, a container that holds data. In this sense, when we say assign or load 1234 into the variable a, it's similar to how we load a value into a register. However, it's important to note that a equals 1234 in Python doesn't represent an equation like it does in maths. In programming, this is an assignment operation, meaning that the value 1234 is stored in the container, variable a. It doesn't state that they're mathematically equal. All the flip-flops in a register are synchronized by the same clock signals, meaning when the clock triggers, the flip-flops update or store their data at the same time. Registers are connected to the CPU's data bus, allowing data to flow in and out of the register. Input signals send data to the flip-flops, and output signals read the stored data. There are different types of registers in the CPU, each serving a specific purpose. General-purpose registers store temporary data, intermediate results, and instructions. Instruction registers hold the current instruction the CPU is executing. Program counter keeps track of the address of the next instruction to execute. Memory address register stores the data of the memory location being accessed. The memory data register holds data being transferred to or from memory. And status registers track flags and condition codes like the 0 flag or carry flag. In assembly language, we use bitwise instructions to manipulate data in CPU registers at the bit level. Common bitwise instructions in x86 assembly include AND clears specific bits. For example, AND AX BX uses the data in register BX as a mask to clear specific bits in register AX, or sets specific bits. For example, OR AX BX sets specific bits in register AX using the bits in register BX. XOR toggles bits if they differ. For example, XOR AX BX toggles the bits in register AX based on the bits in register BX, and NOT inverts bits. For example, NOT AX inverts all the bits in register AX. These operations modify individual bits of data stored in registers, allowing the CPU to process data more efficiently. In high-level languages like C, C++, and Python, bitwise operations are represented by the following symbols. And the symbol is and it performs a bitwise AND operation. Or the symbol is vertical line, and it performs a bitwise OR operation. XOR, the symbol is caret, and it performs a bitwise XOR operation. And NOT, the symbol is wavy line, and it inverts all the bits. Let's walk through an example where we clear and set specific bits using bitwise operations, both in Python and x86 assembly. We start by defining two numbers in Python. The number A is set to 12, which is 1100 in binary. The mask is a value that will help us manipulate the specific bits of A. In this case, the mask is 5, which is 0101 in binary. Now let's see how this would be done in x86 assembly. We use the move instruction to load the values 12 and 5 into registers. In this case, we'll load 12 into the AX register and 5 into the BX register. In x86 assembly, the destination register, where the value goes, is on the left, and the data or source is on the right. So in the first instruction, we're putting the value 12 into the AX register, and in the second instruction, we're loading the value 5 into the BX register. Next, we use a bitwise AND operation to clear specific bits in A in Python. By using the mask, we can clear any bit where the mask has a 0. In this case, the result will be 4, because the second bit from the right is cleared. Let's see the result when we print it. It will be 4 in decimal, 100 in binary, and 4 in hexadecimal. This same operation in x86 assembly would look like this. Here, we use the AND instruction to clear bits in the AX register, where the corresponding bits in BX, the mask, are 0. Now let's use a bitwise OR operation to set specific bits for the same two numbers A and mask in Python. Wherever the mask has a 1, the corresponding bit in A will be set to 1. In this case, the result will be 13, or binary 1101, since the second bit has been set. You can also print this result. It will be 13 in decimal, 1101 in binary, and D in hexadecimal. In assembly, the same bitwise OR operation would look like this. The OR instruction sets bits in the AX register wherever the corresponding bits in BX, the mask, are 1. These bitwise symbols, and vertical line, caret, wavy line, are common in many programming languages like C, C++, Python, Java, JavaScript, and PHP. In languages like SQL and BASIC, you might see keywords like AND, OR, XOR, and NOT, which are conceptually similar to the x86 assembly operations we've discussed. This demonstrates how bitwise operations can efficiently manipulate individual bits across different languages and platforms. One important detail in both low-level and high-level operations is the synchronization by the clock signal. When performing operations on registers, such as the bitwise AND and OR examples above, the clock signal in the CPU ensures that all bits are updated at the same time. In the case of Python, this process is abstracted away, but under the hood, the CPU's clock drives these operations at the hardware level. Understanding this connection is crucial for tasks like low-level programming, encryption, and performance optimization, where bitwise operations are often used to work with individual bits efficiently. Since these operations happen at the logic gate level in hardware, they're significantly faster than software-based implementations. You can try out the Python code in juniorit.ai's playground to gain hands-on experience with how bitwise operations work. When we talk about 64-bit operating systems, or software, we're referring to systems or programs designed to run on a 64-bit CPU. A 64-bit CPU means that the general-purpose registers of the processor are 64 bits wide. This allows it to read or write 64 bits or 8 bytes of data at once. In contrast, a 32-bit CPU has registers that are 32 bits wide, meaning it handles data in 32-bit chunks. For example, if you write a simple Hello World program in C and compile it on a 64-bit Linux machine using the default GCC compiler, the resulting binary will be built to use 64-bit registers by default. In assembly language, the names of 64-bit registers differ from those in 32-bit systems. For example, in an x86 32-bit CPU, the EAX register is used, but in an x86 64-bit CPU, its equivalent is the RAX register, which can hold 64 bits of data. This is why a binary built for a 64-bit CPU can't run on a 32-bit machine. The register names and sizes are different. However, if you want to compile your code for a 32-bit system on a 64-bit Linux machine using the default GCC compiler, you can add the flag gcc-m32 to compile the binary in 32-bit mode, provided the necessary 32-bit support libraries are installed on your system. This is why 32-bit software can run on a 64-bit operating system, but the appropriate support libraries are required. Generally, a 32-bit program should be able to run in a 64-bit Windows system without any problems, and you can also run a 32-bit software on 64-bit Linux if the necessary libraries are installed. However, on Mac OS, starting from Mac OS Catalina, 32-bit software is no longer supported, meaning only 64-bit applications can be used. Here are a few prompts to explore more about 32-bit and 64-bit software and CPU registers. How can I build 32-bit software on a 64-bit Ubuntu Linux system? What's the difference between 32-bit and 64-bit software? Why are 32-bit systems still important even though most computers and mobile phones today are 64-bit? What are the differences between register names in x86, 16-bit, 32-bit, and 64-bit CPUs? You can find these AI prompts in the assignment for this video. The Arithmetic Logic Unit, ALU, is a core component of the CPU, responsible for performing arithmetic operations like addition, subtraction, multiplication, and division, as well as logic operations. When performing an addition, the data to be added is first loaded into the CPU's registers. The ALU then uses logic gates, typically full adders, to add the numbers bit by bit. A full adder works by using an XOR gate to calculate the sum of two bits, an AND gate, and an OR gate to handle the carry for the next higher bit. Once the addition is complete, the result is stored in a destination register, which holds the sum of the two numbers. After an operation like addition, the ALU may set various status flags. The 0 flag indicates whether the result is 0. The overflow flag indicates if the result is too large to fit within the number of bits available. For example, in a 4-bit signed number system, the first bit is assigned to mark positive or negative. If we look at binary 7 plus binary 1, which is equal to binary 8, where the first bit of binary 8 is 1, causing the value to become negative, the two positives make a negative, which can't be equal, therefore causing an overflow. The carry flag tracks whether there's a carry out from the highest bit. For example, in 4-bit unsigned numbers, the binary 15 plus binary 1 is equal to binary 16, which becomes 5 bits, but only 4 bits are available, so a carry out occurs. In most high-level languages, the addition operation is represented using the plus symbol, similar to basic arithmetic. Here's an example in Python. In this Python example, we initialize the variable a with the value 1, then add 2, and finally print the result, which will be 3. The code will be interpreted by the Python interpreter into machine-level instructions at runtime, which is similar to the x86 assembly code. Using the add instruction for addition is shown below. In an ALU, subtraction is often handled using a method called 2's complement, which allows subtraction to be performed as an addition operation. To subtract b from a, you can convert it into addition. A minus b equals a plus negative b. To find negative b, or the 2's complement of b, you can do it in 2 steps. Step 1, invert all the bits of b, and step 2, add 1. Here's the Python code that demonstrates this implementation. In most high-level languages, the subtraction operation is represented using the minus symbol, similar to basic arithmetic. Here's an example in Python. In this Python example, we initialize the variable a with the value 3, then subtract 2, and finally print the result, which will be 1. The equivalent x86 assembly code uses the sub instruction for subtraction as shown. In an arithmetic logic unit, ALU, multiplication and division are more complex than addition and subtraction, but they're still based on basic operations, like shifting, adding, and subtracting. Modern ALUs use optimized algorithms to perform these operations efficiently. But what is shifting? Shifting is a key concept in binary maths. It works similarly to what happens when you multiply or divide a number by powers of 10 in base 10. For example, if you multiply an integer by 10, the digits move to the left and zeros fill in on the right. If you divide by 10, the digits move to the right and we can just omit the leading 0 in the left. In binary, it's the same idea when multiplying or dividing by powers of 2, which is called shifting. Left shift moves all the bits to the left, which is like multiplying by 2. Right shift moves all the bits to the right, which is like dividing by 2. In digital circuits, shifting operations are essential for tasks like multiplication, division, and bit-level data manipulation. There isn't a specific shift gate, but shifting can be done using a combination of logic gates like AND, OR, NOT, multiplexers, and flip-flops. These elements are often used in components like shift registers or barrel shifters to perform shifting efficiently. In assembly language, shifting is performed using the SHL shift left and SHR shift right instructions. Here's an example of shifting in x86 assembly. In Python and languages like C or C++, shifting is done with the operators double less than sign, which is left shift, and double greater than sign, which is right shift. These operators multiply or divide by powers of 2, respectively. Here's how you can shift bits in Python. In x86 assembly, multiplication and division are performed using the mul for multiplication and div for division instructions. Below is an assembly code example. As you can see, both multiplication and division use the AX register, not just to store the result, but also as the multiplicand and dividend. In x86 assembly, we rely on the AX register, known as the accumulator for these kinds of operations. It's designed to be super efficient at handling and processing data during calculations, making it the go-to register for arithmetic tasks. In high-level programming languages, multiplication and division are represented by the asterisk and slash operators. Let's take a look at an example using Python. In this example, multiplying 4 by 3 gives us 12, and dividing 12 by 3 returns 4.0, not 4. That's because in Python, the slash operator performs float division, meaning the result is always a floating point number. If you want to get an integer result, you need to use double slash, which performs integer or floor division. Now here are some AI prompts to help you further understand key operations like floor division, ceiling, and modulus in Python. How to perform integer division in Python, which rounds down to the nearest whole number. How to round a number up to the nearest whole integer in Python. How to get the remainder of a division in Python. In C language, there isn't a built-in function to print a number in binary format, but we can use right shift and AND operations to print each bit. For example, if we want to print the third bit from the right in the binary number 0111, we can use the following C code. By right shifting the number by 3, and then using a mask, we can isolate and print the last bit. Bitwise operations are also very useful in MCU, microcontroller unit GPIO applications, such as controlling LED lights. In an MCU, GPIO registers map to specific registers in the hardware. Controlling an LED means setting or getting a specific bit in the corresponding register. Here's an AI prompt to learn how to control an LED using bitwise operations in an MCU. I have a microcontroller with 8 pins. each connected to an LED. There's a register, R10, in the MCU that controls these pins. It's an 8-bit register, so each bit controls one pin. If a bit is 1, the LED is on, and if it's 0, the LED is off. How can I check if the 5th pin is on or off? And how can I turn on the 4th pin? As you can see, once you understand the concept, you can use AI to help you with related coding tasks. Even if you don't have any MCU hardware coding experience, you'll be able to easily read and verify the AI-generated code, as you'll understand how it actually works. You can find this prompt in the assignment accompanying this video. XOR logic gates have a cool feature. They can be used for data encryption and decryption. Let's say you have some binary data you want to keep safe. We'll call this your plain data. To encrypt it, you can pick a random binary key that's the same size as your plain data. When you run an XOR operation between the plain data and the key, you get the encrypted data. And to decrypt it, you just run XOR again between the encrypted data and the same key. It works like this. Now let's look at some Python code to see this in action. After encrypting and decrypting using the same key with the XOR operation, the output will indeed be the original plain data. Using this method, XOR gates can serve as a simple hardware-level encryption tool. For larger data, you can break it into chunks the same size as the key and encrypt each chunk. This process is fast, making XOR an efficient option for basic encryption. But think about what happens if your plain binary data has a lot of consecutive zeros. In that case, parts of your encryption key will be visible in the encrypted data after the XOR operation, which makes it vulnerable. That's why XOR encryption can be easy to crack, unless you follow a few important rules. 1. The key must be completely random. 2. The key must be the same length as your data. And 3. The key can be used only once. This is called one-time pad, OTP encryption, and is theoretically unbreakable if done right. OTP was invented back in the early 1900s. The key was written down on paper pads with random numbers or letters. After using a key once, they destroy it to keep it safe from being reused. Even though OTP is unbreakable in theory, it's tough to use. First, key management. Distributing and keeping the key secure is hard, especially with large amounts of data. And second, randomness. Most computers use pseudo-random numbers, which aren't completely random, and could make the encryption weaker. That's why modern encryption algorithms like AES, Advanced Encryption Standard, are more practical. AES uses complex steps to protect data through confusion, making it hard to find links between the data and the key, and diffusion, ensuring that changing even one bit in the data changes the whole encrypted message. AES has a fixed key size, 128, 192, or 256 bits, and unlike OTP, the key doesn't have to be as long as the message, which makes it way more practical for everyday use. In the description of this video, you'll find a link to join our Discord server, where you can receive hands-on support and explore all the concepts we discussed today in greater detail. Our AI assistant, ByteMate, will guide you through an interactive assignment that includes AI prompts related to this session, helping you dive deeper into Bitwise operations and other topics covered. In the assignment, we'll guide you step by step through a real project with the help of the ByteBoss AI agent. You'll get hands-on experience with encrypting, decrypting, compressing, and uncompressing binary data, solidifying your understanding of the CPU and bit-level data processing. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you never miss our upcoming lessons on Linux, AI, and full-stack coding development. See you in the next video!